Section 11.6 talks about absolute convergence, ratio, and root tests. These are the last tests that we learned in this chapter. And then later we're going to learn how to apply them. Because it talks about the absolute values, good to recall that the absolute value of negative 1 to an n, it's going to be 1. Negative 1 to an n plus 1, it's also 1. Negative absolute value of negative 1 to an n minus 1 is also 1. So negative 1 to any power, when we take the absolute value for that, that's going to turn it to be positive 1. So when we take the absolute value of a sequence like this within the series, that means I'm summing up all the absolute values terms of that sequence at some point an, and that keeps going forever. Those are quick hints or information you need to know. Now, what does it mean to say absolutely stuff? What is absolute stuff? So we introduce a definition for this. What does the definition say? So we say a series, let's call it an, as n goes from 1 to infinity, is absolutely convergent if the series of absolute values this one, the series of absolute values, is convergent. So again, a series is called absolutely convergent if, when we take the absolute value of this, it converges. So when we take the absolute value of its term, it converges. For example, let's say negative 1 to an n plus 1 divided by n. N goes from 1 to infinity. We need to test if this series converges or diverges. How about make it 4 here? So we're going to test if this series converges or diverges. Now, you can, if you want, because it's an alternating series, you can start by using AST, right? Check if it's decreasing and check if the limit equals to what? 0, right? You can check that out. Now, if I take the absolute value for this, what happens? So if I do absolute value of this, the absolute value will clean up all these negative 1 to any power. So that will give me 1 over n to the 4th. So what do I know about this? This converges by p test, because p is bigger than 1, p equals 4. Since the absolute value of that converges, then the given series, the one in blue that you see, then the given series converges absolutely. So at the end, we are interested to see if it converges or diverges. But on the top of that, we added the absolutely convergent. Also, we're going to add another term, a series, same series, an goes from 1 to infinity, is called conditionally convergent if it converges but not absolutely convergent. For example, this series. We're going to test if this series converges or diverges. So you know this is alternating series, right? If I do exactly what I did in the previous example by taking the absolute value of negative 1 to an n minus 1 times 1 over n, the absolute value will clean up all that negative 1 to that power, right? What do you think about this series that we got? Does this converge or diverge? Yeah, this one diverges by the p-test. We call it harmonic series because p is 1. If p is 1 or less than or equal to 1, diverges. Bigger than 1, converges. So this diverges. So what happened? When I took the opposite value, it's not convergent. It diverges. How about itself? Can I test it by using the AST? So how do I check the AST? First thing, we have the AN, 1 over n. AN plus 1, you can use derivatives or you can use this. This is much easier and quicker. Notice the larger the denominator, the smaller the fraction. So what I have here, AN plus 1 is less than or equal to AN for n bigger than or equal to 1. So that tells me it's decreasing. This was done back in section 11.1. So it's decreasing. And what's the other thing we need to check? The limit, right? The limit of AN. The limit of AN as n approaches infinity equals the limit of 1 over n, which is 0. So notice the two conditions of AST are met. Then it converges by AST. So now what happened? When we try to test if it converges or diverges, it converges by AST. And when we did the absolute value, it diverges. That is called conditionally convergent. Conditionally convergent. So it is conditionally convergent. So again, if we look back at the definition, watch. It says it converges conditionally when? If it converges, as I did with AST, so that converges usually happened by using AST, but it's not absolutely convergent. So it means when you take the absolute value, it doesn't converge. So I took the absolute value, it doesn't converge. But when I use AST, it converges, so it converges conditionally or conditionally convergent. Any questions up to this point? Let's look at this example. Let's say cosine n over n squared. N goes from 1 to infinity. Let's take the absolute value. So when we do the absolute value of this, cosine n over n squared, what do I know about cosine, the absolute value of cosine? Well, we know the absolute value of cosine x in general is always less than or equal to 1, right? So this is less than or equal to the sum of 1 over n squared. Right? Because on the right side, if you divide both sides by x squared, because it's positive, and you do the sum, that's where that came from. So now what do you know about this series? The underlined series. This one converges by the p-test. Now what can I say about this one? Then that one, what happened to it? Converges by what? By the comparison test, because the bigger converges, the smaller has to converge. So when I did the opposite value, it converges. So when I took the opposite value, it converges. So what happened? Then the given series converges what? Absolutely. So let's do a summary stuff. Summary about the procedures. What's the procedures? So always when you see a sequence with -1 to an n, or -1 to n plus 1, -1 to n minus 1, or some special cases like cosine or sine, okay? So the first step is you take the absolute value, okay? So first, so a sequence is given. So what do? You take the absolute value. Take the opposite value. And there are conditions here. If the opposite value converges, then the given sequence converges absolutely. The other case, if it diverges, then use the AST. Use the AST. Use the AST. Now, when you use the AST, what happens? It can converge or diverge, or we don't know what's going to happen there. But if it converges, then we say the given series converges what? Conditionally. Let's look at the next example. The sigma of -1 to n minus 1 square root of n over n plus 1, where n ranges from 1 to infinity. First thing, we're going to take the absolute value of this. Which will clean up the -1 to n minus 1. Nothing happens to the square root of n plus 1 because those are always positive. N goes from 1 on. So now how are we going to check if this converges or diverges? So you can do p-test. I don't want to do integral test. That's the last option. Comparison would be a little bit difficult, or it might not work. It's not geometric series test. So what we can do is, maybe I want to try the limit comparison test by finding another series, which is this one, the sequence, that's n to the 1/2 over n, so that's 1 over n to the 1/2. Now we find the limit of an over bn as n approaches infinity. Limit that's an, over means you multiply by the reciprocal. This will go to 1, this will go to 1. So that gives me 1, which is bigger than 0 and finite, if you remember the limit comparison test. But we know that the sum of Bn, which is the sum of 1 over n to the 1/2, diverges by the p-test. This means so that series also diverges by the limit comparison test. So I know it diverges when I took the absolute value. Since it diverges, based on the procedures, we need to find out if it converges or diverges by the AST. Now, we do two things. Remember, an is the square root of n over n plus 1. We transform this into a function in x, and we find its f prime, which I'm assuming everyone can find out. It will turn out to be 1 minus x. So when x starts at 1, 1 is 0, but from 2 on it will be negative. So this will be less than 0 for all x bigger than or equal to 2. So this tells us it's a decreasing. And we need to find the limit of an as n approaches infinity, limit of the square root of n over n plus 1. But notice this goes to infinity over infinity. We can use the easiest way, use L'Hopital's rule. So L'Hopital says derivative of the top over derivative of the bottom, and this goes to 0. So notice the two conditions of the AST are met. The two conditions are met. So it converges. It converges by AST. Since when we took the absolute value diverges and it converges by AST, then the given series converges conditionally. So let's close the first half of this section with the theorem. The theorem said if a series converges absolutely, then it converges. That's the first half of the section. The second half covers two new tests called ratio test and root test. And then we're done with all these convergence, divergence tests. So let's start with the ratio test. We're going to be using this a lot from now on. The ratio test, very important. It says you find the limit as n goes to infinity of the absolute value of an plus 1 over an. Keep in mind, some people, they do the other way. They put an on the top. That will change everything. But you do this, and then let's say you get L, like a number L. If the number L, if L is bigger than 1 or infinity, then it diverges. If L is less than 1, then converges. if it's equal to 1, we say inconclusive. Inconclusive means I cannot draw any conclusion about this test, this series, if it converges or diverges. Now, how do I know I should use ratio test? Is there any hint, something that can help me, any indications? Well, the way most of the time we use the ratio test, so we say the ratio test is mainly used when the sequence or the series contains either a factorial term or a number to an n, like 2 to the n, 5 to an n term. When I see either one of them within my series, that helps, like, okay, I think I need to try the ratio test. And of course, after this, you want to check for convergence, divergence. Let's say -1 to a k, 2 to the k over k factorial. K runs from 1 to infinity. We're going to check if this converges or diverges. But before we do this, let me comment back on the value of L. What about the value of L? Well, again, as I said, some textbooks, they might tell you find the limit as n goes to infinity of an over an plus 1. If they flip it, then things get flipped. Then when L bigger than 1 converges, when it's less than 1 diverges. Make sense? So make sure you always follow the same thing. An plus 1 goes on the top. Now here, what is our an? Here we have ak. ak is the -1 to the k times 2 to the k over k factorial. Then we're going to find a sub k plus 1 by replacing every k with k plus 1. 2 to the k plus 1 over k plus 1 factorial. That's a sub k plus 1. Then I'm going to find the limit as k goes to infinity of a sub k plus 1 over a sub k equals limit as k goes to infinity. A sub k plus 1 is -1 to the k plus 1 times 2 to the k plus 1 over k plus 1 factorial divided by a sub k. So what you could do multiply and flip that a sub k. -1 to the k, 2 to the k. So always do multiplication, flip the a sub k. So the first thing we can get rid of here, the -1 to those k's, because the absolute value will clean them up. Right? Other than that, I don't see anything simplifies, but see what we're going to do now. So it's going to go limit as k goes to infinity. The 2 to the k plus 1, you can do 2 to the k times 2 to the first power. Times here, k factorial over 2 to the k. Now the k plus 1 factorial, which one is bigger, k plus 1 or k? Is k plus 1. We always keep the smaller the same. This is the smaller. Keep it the same. What I'm going to do with k plus 1 factorial, I'm going to write it k plus 1 times k factorial. So then these cancel out. And not only that, the 2 to the k cancel out. So now I'm only dealing with the limit as k goes to infinity on the top 2, the bottom k plus 1. So a number over infinity, that's going to go to 0, which is less than 1. That tells me that the series, the given series, converges by the ratio test. Let me give you another example. You're going to try it on your own. -1 to the k times 2k minus 1 factorial over 3 to the k. K goes from 1 to infinity. Okay, so we're going to use the ratio test. So we need to find the limit as k goes to infinity of a sub k plus 1. So replace every k with k plus 1. When you replace the k with that, you get 2k plus 2 minus 1 over 3 to the k plus 1 times, you flip the given sequence. And this one here becomes 2k plus 1 factorial. So again, these cancel. So what we need to do is, for the denominator here, you write it as 3k times 3 to the first. Keep the top the same. For the factorial ones, like this one and this one, the denominator is smaller, 2k minus 1 factorial. I'm going to take the top one and rewrite it as 2k plus 1, subtract 1 becomes 2k, another one, 2k minus 1, and that's where I stop. So then this cancels this, as you can see. And this cancels this. Let's see what is left. Limit as k goes to infinity. On the top, I'm left with 2k times 2k plus 1, and the denominator is just 3. So this would go to what? This would go to infinity, right? Nothing in the denominator, so that goes to infinity. So what does that mean? So this goes to infinity. It means it diverges by the ratio test. It diverges by the ratio test. To practice more on this, try another one. Negative 2 to the n times n squared all over n plus 2 factorial. N runs from 1 to infinity. Check if this series converges or diverges. So we find the limit as n approaches infinity of an plus 1 over an. So every time you do the problem, write it down, so this way you don't forget. So equals limit as n approaches infinity. Replace every n with n plus 1. So n plus 1 squared divided by n plus 3 factorial times, flip the given sequence. Now we need to do some rewriting. The negative 2 here is negative 2 to the n times negative 2 to the first power. Keep the n plus 1 squared for now. This stays the same. The top, the n plus 2 factorial, is the smaller. The n plus 3, you do n plus 3 times n plus 2 factorial. Then we're going to simplify the n plus 2 factorial and negative 2 to the n. Right? To be able to find the limit, what we can do, the negative here is going to go away and keep the n plus 3 the same. I'm going to group this and this together like so, n plus 1 over n squared. Why did I do that? Because when I pass the limit inside by the limit laws, the first one will go to 0. And the second one, the inside, is 1. The limit of this is 1. 1 square. So that's 0, which is less than 1. So since it's less than 1, it converges. You can say converges absolutely if you like, and hence converges, or you can just say it converges by the ratio test. The next test is called the root test. Root test. So the root test says you find the limit as n approaches infinity of the nth root of the absolute value of an, just the nth root of that. And let's say we got L. Now depending on L, if L bigger than 1 or infinity, then it diverges. Same thing as the ratio test. If L less than 1, converges. If L equals to 1, inconclusive. First one, 2n plus 7 over 5n plus 1 to the nth power. N goes from 1 to infinity. To apply like the ratio test here is not going to be easy or impossible. It's not a geometric series test. It's not a p-test. You can't do AST. Like all the tests that we've taught you already is not going to work out. So how do I know I'm going to use a root test? When you see the nth power or n square or 2n or something to an n power. So that indicates that we could use the root test. So how do I use the root test for such an example? We start by finding the limit as n goes to infinity of the nth root of what we have or what is given, and algebraically the n and n, they cancel each other. So now all I'm doing is I'm just finding the limit of 2n plus 7 over 5n plus 1 as n goes to infinity. And what is this limit? You can see it's going to give you infinity or infinity. We could use L'Hopital, or if you know from before, from Calc 1, is going to be 2 over 5. So you just say 2 over 5. That is less than 1. Since it's less than 1, it converges absolutely and hence converges by the root test. And it's called root test because the nth root, we're finding the nth root. Check if this series converges or diverges. Negative 2n over n plus 1 to the 5n as n goes from 1 to infinity. Notice in the previous one I didn't put absolute value because I knew like the 2n plus 1 is positive, 5n plus 1 positive, so nothing to worry about to put absolute value. So here we start with limit as n goes to infinity of the nth root of the absolute value of an. So limit as n goes to infinity, the nth root of the absolute value of negative 2n over n plus 1 to the 5th power of n. So that absolute, the 5n, the n will cancel with the n, and the absolute value will cancel that negative sign. That will leave positive 2n over n plus 1 to the 5th power, because 5n over n is 5. And by the limit laws, we can pass the limit inside as n approaches infinity. The inside gives me 2 to the 5th, 32. So that's bigger than 1, means diverges by the root test. by the root test. Another example on this, the sum of n plus 1 over n to n square as n goes from 1 to infinity. Test if this series converges or diverges. So we find the limit as n goes to infinity of the nth root of the absolute value of an to the nth power. So we do limit n goes to infinity of the nth root of n plus 1 over n square. So the way this works is if you divide the n square inside by the n out, that would be n plus 1 over n. N squared divided by n is n. Now if you pass the limit inside, you're going to get 1 to infinity, which is indeterminate, is not 1. So the trick around this is to split the stuff inside into n over n1 plus 1 over n to n. And guess what that is? This is the definition of E, the 2.7. That's what it is. So E is bigger than 1, diverges by the root test. By the root test. So a question would be, how about if the limit is 1? So that's, let's write it as a note. If the limit of, let's say, the nth root of this as n goes to infinity, or the limit of the root test or ratio test is 1, then we say these two tests are inconclusive. In this case, we need to use a different test. So it could be like integral test, could be limit comparison test. So that's what inconclusive means. We cannot draw a conclusion using the root test or ratio test. So that's why we have to try a different test. Now, which test do I need to know? All this comes with experience. All this comes with experience. The more you practice, the better for you. The more you practice, the better.